the previous lecture we were discussing about the concept of entropy generation and its physical understanding. So, with this background we will learn about a very important principle, which is principle of increase of entropy. So, let us say that you have a thermal reservoir which maintains its temperature T naught, and there is a heat transfer from this to a system which is del Q, and the system temperature it changes based on the heat transfer. So, the temperature at the system boundary is T, which is different from T0. So, then you can write ds of the system, if you consider this as your system, as del Q over T. What is ds for the surroundings? This is the surrounding, which is the thermal reservoir. If the equality for reversible, inequality for irreversible. What is ds for the surrounding? For the surrounding, the heat transfer is minus del Q. So, if you when you are writing it for a system, you have to imagine a surrounding, you have to imagine the surrounding as the system. So, for surrounding as a system, the heat transfer is minus del Q, its temperature remains constant, and because it is a vast thermal reservoir, it can be considered to be a reversible process for the surrounding. So, ds system plus ds surrounding, this is greater than equal to del Q 1 by T minus 1 by T0. Can you tell for a heat transfer to be feasible which one is more, T or T0? Definitely T0 is more. So, T0 is greater than T. So, 1 by T is greater than 1 by T0, right. That means, and del Q is positive. So, ds system plus ds surrounding, it is greater than equal to 0. System plus surrounding together is called as universe. So, ds universe is greater than equal to 0. This is called as principle of increase of entropy. So, with every process taking place in the universe, the entropy is continuously increasing. This may give, with every statement we make, we have to be careful. I have seen students interpreting this as entropy always increases during a process. So, this is entropy of the universe. Entropy of the system may increase or decrease, because you look at this expression, S2 minus S1 is equal to integral of del Q by T plus S generation. This is S2 minus S1 of the system. So, when can entropy of the system decrease? See, this is always positive. no doubt about it. It can be 0 in the minimum. Integral of del q by t, this can be positive or negative depending on whether del q is positive or negative. So, this is plus or minus depending on whether del q is plus or minus. So, sum of these two can really be anything, plus, positive, negative, 0. If the sum of these two is positive, then entropy of the system increases. If sum of these two is negative, that means entropy of the system decreases, and if sum of these two is 0, that has two possibilities. One possibility is this is 0 and this is 0, that is reversible adiabatic process. So, change in entropy equal to 0, one possibility is it is reversible adiabatic, but there is another possibility. What is that? Let us say this is minus 10 and this is plus 10, then also it can be 0, but that is not reversible adiabatic. So, change in entropy during a process equal to 0 does not necessarily mean that it has to be reversible adiabatic, right, that you have to be very clear about. So, here the change in entropy of the system plus that of the surrounding, that is greater than equal to 0. So, entropy continuously increases, that is true, but it is not entropy of the system as just like that, it is the entropy of the system plus surrounding, that is entropy of the universe. So, this again is a very important concept that we have.
ds surrounding equal to minus del q upon t naught. Why did you write an inequality?
So, normally you know this surrounding that we are talking about, it is undergoing a reversible isothermal process. So, this temperature, see this is an example where we are having a fixed T0 but variable T. So, typically why we are writing this is because we are normally considering the surrounding as a thermal reservoir, that is the common thermodynamic situation, and when the surrounding itself is a thermal reservoir, for any thermodynamic process you will always have a thermal reservoir, may not be the immediate surrounding, but the ambient which is outside the immediate surrounding. So, that thermal reservoir is correctly represented by this equality rather than inequality. So, that is why this equality is used here, because for the thermal reservoir, see you can indefinitely add or subtract heat without much change. So, it is a very slow heat transfer with constant temperature. So, for the surrounding it is like a reversible isothermal process. Now, we have discussed so much about entropy, and the funny thing is that even after all this we have not really understood what is entropy, and this is always a candidate fooling question. So, I have seen that in many interviews the people who are asking questions, so the candidate appears in the interview, and after appearing for the interview the examiner with a very nice smile says, what is your favorite subject? This poor candidate, maybe he has done so well in his thermodynamics courses, or she has done very well in her thermodynamic courses. So, quickly he or she says that thermodynamics is my favorite course, and then you are under trap. So, then the next question is, have you heard what is entropy? And of course, anybody who has done thermodynamics will at least know what is that, there is a term called entropy. So, then the next question is an obvious extension, can you explain what is entropy? And then I mean it is always easy to ask these questions, it is very difficult to give answer to this. The privilege of the examiners is that they sit in the other side of the table. So, they can ask anything, and they can expect that at an age where when people are not that matured, they are expected to give a very matured generalized answer of what is entropy. It is very difficult, because again as I told you in the very beginning that understanding second law, entropy, all those things is like by visualizing an elephant from different angle, like whether you are looking at the ear or tail or whatever, based on that you give your own interpretation. So I will like to give you some interpretations, and these are based on some interpretations of entropy in some chosen fields, but you have to understand clearly that this does not cover everything. So just to divert a little bit from the same thing, heat transfer, work done for long. So what I would do is I would like to give an example of information theory. So entropy is a very important concept used in information theory. I am not a specialist in information theory, but I can just give you certain analogies which have equivalent presence in classical thermodynamics. So in information theory there is a terminology which tells you that how much information is contained in a given data. So I mean why do you need it? So let me give you an example. Let us say that many people have this habit, after waking up in the morning they will look into the smartphone or computer and browse the latest news in their favorite newspaper. So the newspaper web page has certain news. So let us say some hypothetical newspaper gives a news, today sun rises in the east. Let us say one sentence, today sun rises in the east. So now this is a fact, I mean you cannot say that this is wrong, but this will not create any sensation. So this the information content within this is very little or no information, I should say. So on the other hand, some news media, just to create sensation, I mean sometimes these kind of things are done also purposefully to create a sensation, some news which discusses about very unexpected event, that unexpected news is brought into highlight. Say somebody writes that sun rises in the west today, I mean very hypothetical, impossible, but I am just giving you an example. I have seen that while travelling in railways that there are wall I mean statements written in the wall that the sun moves around the earth, and this has caught attention of many people because this is something which contradicts their learning in education. So this will create immediate sensation, although people might later on realize that is not correct and so on, but who will verify? I mean before verifying, the number of clicks, the so called likes in our I mean social media pages and all those things will blow up like anything, and this is what people want. These days people are more concerned about how many likes do you get in social media rather than what is the seriousness of what you are interested to convey. So to bring the bottom line here, the amount of information is proportional to log of 1 by probability of occurrence of an event. Okay. So if you have a event with very low probability, 1 by low probability will make it a large number and log of that will be large and therefore the information content will be high. So there is a definition of entropy of information associated in information theory. This is summation of this is basically a weighted average of the information content. Okay. So this is called as entropy of information. So you know more entropy of information will essentially implicate that you know it is information rich. So then this is information theory. Now let us consider an equivalent thermodynamic, classical thermodynamic situation when we have a system with a total energy, volume, temperature etc., but this system has many. So this is a macroscopic state when we say the system has a particular temperature, the system has a particular energy, particular volume, this is a macroscopic picture. Now there could be many possible microscopic states that could at the end give rise to a final same macroscopic picture. So let there be n number of possible microstates. For a given macrostate. Okay. So you give more freedom, there will be more number of such microstates. If you give less freedom to the system, if the system is more constrained, there will be less number of macrostates, microstates. So now if you relate that what is the probability of occurrence of each of the microstates, then that can be linked with this one with the probability of occurrence of each microstate as 1 by n, because there could be n number of possible microstates, each of these microstates could be equally probable, I mean there is no bias between these two. So probability of each microstate is 1 by n. So then you can have a weighted average, so you can have a similar definition of entropy which will be now proportional to, so ln of n 1 by pi will become n and summation of pi each is 1 by n and this is summed over n number of possible states, so that will be n by n. So it will be proportional to ln n. Normally this is what is called as Boltzmann's concept of entropy from a microscopic angle. Now the problem is that when we work with classical thermodynamics, the entropy relates to what? See, entropy relates to heat transfer by temperature, right, that is the unit. So that unit does not match with this. To match with this unit, Boltzmann proposed a definition that this proportionality is blocked or is covered by this constant which is the Boltzmann constant. So this is the Boltzmann constant. So this is roughly what, so this is the universal gas constant divided by Avogadro number. So this will be what, 1.38 into 10 to the power minus 23 joule per Kelvin, right. So now this entropy into temperature will become energy unit, joule. So this Boltzmann constant was introduced just to bridge this probability theory based definition with the classical definition of entropy through work and heat, and this is called as Boltzmann's entropy. So, this is how it is interpreted in microscopic thermodynamics, but it all depends on the specific level of interpretation that you give. Now, based on this, what can we say? We say that now if it is a highly ordered system, then the number of possible microstates is less, because if the system is very ordered, it is very constrained. So, it will not be chaotic type where there is a large number of possible microstates. For example, you think of a regimented soldier, a regiment of soldiers, they are very ordered. So, everybody will do the exercise in the regiment of soldiers in exactly the same way, and this is perfect order. In a military, when the training is taking place, you will find that they are so regimented, they will follow exact order. Exact disorder, you imagine a junior school and there is a lunch break or tiffin break after the class. All the young kids will come out of the class, literally they will jump out of the class and float around, run around using whatever space that is there in the school lawn, and that is absolute disorder. So, why that is absolute disorder? Because there are large number of possible microscopic states. Every student, every child can act in his or her own way, but eventually there is a macroscopic state that is there prevailing in the school, and that macroscopic state is defined by the tiffin hour. Within that, there is a chaos and large number of possible microscopic states. So, that is a highly disordered system. If you imagine a thermodynamic system, a partition on one side gas, another side vacuum, you allow the gas to expand freely, and that is perfect disorder, because the gas will randomly spread across all. But if you constrain it to move in a quasi equilibrium process, then it is more regimented like the soldier. So, we can understand that more is the disorder, more is the number of possible microstates, and more is the number of possible microstates, greater is the entropy. So, to summarize, we can say that entropy is a measure of disorder, and because the change in entropy of the system and surrounding together or the universe is positive, that means we can summarize that disorder is increasing in the universe in some way or the other. So, why disorder is increasing? Because it is more natural to have disorder rather than order. If you keep a system freely, the system will naturally choose disorder. I have seen that on one day I have organized my office very nicely, all the files on one side, all the books on one side, all the pens on one side, maybe the board eraser on one side, the marker pen on another side, all the theses that I have examined on one place. So, it looks very nice. So, I have given a lot of effort to do that. After 7 days, I find that with whole lots of files and papers submitted by my students to correct and this and that, the entire office is in disorder. I have not given any special effort, but the system has actually preferred to go to a disordered state spontaneously. So, having a disorder is more spontaneous than having an order. So, and this leads to one of the very important definitions, the definition of absolute entropy. The definition of absolute entropy is governed by the third law of thermodynamics, and I will briefly talk about this. In this particular course, we do not have a provision of discussing about the third law of thermodynamics, but what it says is that entropy of a perfectly crystalline substance is 0 at absolute 0. So, this is very important because the second law as such does not define entropy, it only it only quantifies the change of entropy, but the third law defines absolute entropy and it is based on this physical understanding that entropy is a measure of disorder. So, at absolute 0 you expect the disorder to be minimum because the thermal energy is not there, but even then there could be disorder because of imperfection within the system. So, if it is a perfectly crystalline substance then it is absolute order, and perfectly crystalline substance at absolute 0 of course is hypothetical, but that hypothetical state is considered to be a state of absolute order and therefore 0 entropy. So, that is what the third law talks about. So, finally, I would like to give you some other example beyond the heat transfer, work done and even information theory, and this is an example of stretching of a spring. This is a very simple example that can relate mechanics with thermodynamics. So, you have a spring like this, by a force F you stretch it. Question is, does its entropy increase, decrease, what does it do? So, now we will use, so let us use this TdS. Now, can we use TdS equal to du plus PdV? In this case not, because PdV is not the relevant work here. What is the relevant work here? F dx, right? Is it positive or negative? See, here work is done on the system to stretch it. So, if work is done by the system it is positive, if work is done on the system it is negative. So, minus F dx. Okay. So, for if it is taking place isothermally then this is 0, if it is taking place isothermally then you have ds dx okay. F is positive, T is positive, absolute temperature, that means as x increases the entropy decreases. So, during stretching of a spring, as it is stretched more and more its entropy decreases. Why? Because when the spring is free it can attain a large number of microscopic states, but when you are stretching it you are making it more and more constrained, you are making it more and more constrained, that means you are allowing less number of microscopic states for a given macroscopic state, and that makes the entropy decrease. So, I hope that I have given you some examples which can illustrate the concept of what is entropy, although it is very difficult to answer as I told, but through examples and by relating various fields we can perhaps attempt to develop a unified understanding of entropy and how it relates to practical processes. Thank you very much.